Good morning, students. So yesterday we had started with the topic hydrocarbons. So we'll continue with the same topic, hydrocarbons. So as we had discussed earlier, so what are hydrocarbons? So hydrocarbons are the compounds made up of hydrogen and carbon. Okay, so hydrocarbons are the compounds which are made up of hydrogen and carbon. So then we had started with the methods of preparation of alkanes, right? So we had seen the hydrogenation reaction. What do you mean by hydrogenation? We are adding hydrogen. We are adding hydrogen across the unsaturated carbon, that is across the double bond. If you add one mole of H2, right, one molecule of H2, you get ethane. And across the triple bond, if you add two, so it requires how many molecules? Two molecules of H2. It forms ethane. Okay, so hydrogenation, addition of hydrogen across the double bond or triple bond to give you a alkane. So these are some of the methods of preparation. So what is the general molecular formula of alkanes? It is CnH2n plus 2, where n is 1, 2, 3, 4, etc. Okay, so this is the first general method of preparation. Then second, we saw Wood's reaction, right? So Wood's reaction, two molecules of alkyl halide reacts with sodium and dry ether, giving you alkanes and sodium halide. So this is a Wood's reaction. Then coal-based electrolysis. So we had discussed about coal-based electrolysis. Grignard reagent. What is Grignard reagent? It is organometallic compound. Okay, organometallic compounds are nothing but your Grignard reagents. RMGX, right? So reduction of alkyl halide. What do you mean by reduction? So you are adding hydrogen with your alkyl halide. Okay. So you are reducing or you are adding. Your reduction is nothing but addition of your hydrogen to your alkyl halide, giving you a alkane in the presence of ZnHCl. So these are some of the reducing agent. So ZnHCl, hydrogen iodide in the presence of red phosphorus, H2 in the presence of palladium. So these are some of the reducing agent. Any one of the reducing agent can be used. Then, so this H, okay, it is kept in, okay, so this is addition of hydrogen. So hydrogen, it is an elemental hydrogen. Okay, so next is decarboxylation. What do you mean by decarboxylation? It is removal of carbon dioxide. Okay, so here what you are reacting, sodium carboxylate. Your sodium carboxylate, it reacts with your sodium hydroxide and calcium oxide. What is sodium hydroxide and calcium oxide? It is soda lime. Okay, to give you a alkane. So this is decarboxylation. Carbon dioxide is there is a removal of liberation of carbon dioxide. Next, so we had seen some of the questions. Okay, we had discussed this. So then we'll start with the physical properties. Okay, what do you mean by physical properties? So physical properties of alkanes are nothing but the melting point, boiling point, okay, density. So these are certain solubility. So these are certain physical properties. So first we'll start with the boiling point. Okay. So boiling point, the boiling point of alkanes increases with the increase in molecular mass. And for the same alkanes, the boiling point decreases with branching. So with the increase in alkane, with the increase in carbon atoms, what will happen to the molecular change? It will increase, right? In the increase, with the increase in the carbon atom. So as you increase the carbon chain, okay, as you increase the carbon chain, what will happen? The molecular mass will increase, and thus what will happen? Boiling point also will increase when you have a straight chain compounds. Okay, then and if you have the same alkane, so if the same alkane they are in branching form, okay, so here you can see your isobutane, you can see your isobutane, right? Butane, this is an, so it is in straight chain form. So whenever it is in straight chain, so the boiling point will be more as compared to that of the branch chain, because as the branching increases, what will happen to boiling point? Boiling point will decrease. So this is with respect to boiling point. So for a straight chain, it will be there will be increase with the increase in the molecular mass, and for the same alkanes, the boiling point will decrease with branching. Then with respect to melting point, okay, with respect to melting point, what will happen to melting point? So N alkanes with even number of carbon atoms have much higher melting point than the next lower N alkanes with odd number of carbon atoms, due to symmetry in even number of carbon atoms. So whenever you are considering the even number of carbon atoms, okay, in a straight chain alkanes, so they are having higher melting point as compared to that of the odd number of carbon atoms. Why? The reason is due to symmetry. Okay, it is due to symmetry in the even number of carbon atoms. If even number are there, what will happen? The number of carbon atoms will be similar, okay, on both the side. So because of that, in even number of carbon atoms, what will happen to melting? It will be higher. So here are examples of one example is propane, another is N-butane. So if you're considering your boiling point, okay, what will happen to the boiling point? Boiling point in propane is less than that of N-butane. Okay, so butane will have more boiling point. Then another example here, okay, so you can see N-butane and isobutane. So as the branching increases, what will happen to this? So N-butane will have more boiling point as compared to that of the isobutane. So these are two physical properties. First is point, second is melting point. Next, we'll see the solubility. So these alkanes are insoluble in water and they are soluble in organic solvent. Okay, why it is insoluble in water? If anything, any compound or any molecule should be soluble in water, they should form what? They should form hydrogen bonding. Okay, it should form hydrogen bonding. But for the molecule to be soluble in water, hydrogen bonding, when it occurs, if one atom will be hydrogen and another will be a highly electronegative atom is present, right? If a highly electronegative atom is present, then there will be what? There will be formation of this what? Intermolecular hydrogen bonding or intramolecular hydrogen bonding. That is, hydrogen bonding will be there present. So but as these hydrocarbons cannot form hydrogen bonding with water, they are insoluble in water. Okay, so this is a reason. What is the reason? Hydrocarbons, they cannot form hydrogen bonding with water. So those, these are insoluble in water. And these are soluble in what? They are soluble in organic solvent. Okay, so this is the solubility of your hydrocarbons. As they cannot form hydrogen bonding with water, they are insoluble in water, but they are soluble in organic solvent. Next, we'll see the chemical properties of your alkanes. Okay, so first is halogenation of alkanes. Halogenation of alkanes. Okay, so what you are doing, you are adding up your halogen. What is the halogen? So see here, methane is taken. Okay, methane is reacted with your Cl2. Okay, methane is reacted with your Cl2 in the presence of H nu. Is what? Light. Okay, in the presence of H nu, then what you get? You get a series of molecules. You can see here it is CH3Cl, then CH2Cl2, okay, CHCl3 plus CCl4. So these are the series of compounds you get here. Okay, so halogenation of alkane. So here you can see, what do you mean by primary carbon? primary carbon. So this methyl group, here you can see methyl group. Right, you can see this methyl group. So this methyl group, it is attached to only one carbon. Okay, so when methyl one carbon is attached to only, so this carbon is attached to only one carbon, so it is called as primary carbon. So it is said to be primary carbon. Now this carbon, okay, now this carbon, when you're talking about this carbon, okay, this carbon, so this carbon, so when you're talking about this carbon, CH2 carbon, so this carbon attached here another carbon and here one carbon, right? So this is called as secondary carbon. It is attached to other two carbons. So this is a secondary carbon. Okay. Then this center one. Okay. This, when you're talking about the center carbon. So this center carbon, this is attached to what? One, this carbon, then here one, two, and here one, three carbons. So it is a tertiary carbon. So this is primary carbon, secondary carbon, and a tertiary carbon. So like this, if carbon atom is attached to one carbon, then it is said to be what? It is primary carbon. If carbon atom is attached to other two carbon atoms, then it is secondary. If carbon atom is attached to three carbon atoms, then it is tertiary. Okay. So here you can see what is the reactivity of halogen towards alkane. So fluorine, right? You know, fluorine is mostly it is highly electronegative, then chlorine, then bromine, and then iodine. So this is the reactivity of halogen towards the alkanes. So reactivity of different type of hydrogen, that is here you can see tertiary. So whenever you have tertiary carbon, so tertiary will be more stable as compared to secondary and then compared to primary. So this is a different reactivity of different types of hydrogen. So the replacement of hydrogen. So what is happening here in halogenation of alkanes? So there are four hydrogens are present. So at each step, what is happening? You can see there is series of molecules which is formed. So first is what? Only replacement of one hydrogen yields you this compound. Okay. Then a replacement of second, it gives you CH2, Cl2. Replacement of third hydrogen, CH-Cl3, and all the four hydrogen, it is CCl4. So the reactivity of different types of hydrogen. So whenever the from tertiary carbon, if the hydrogen, so it will be more stable. So this, if the replacement takes place at the tertiary carbon, it will be more stable. So halogenation of alkane. So this is the first chemical property. Okay. Next is nitration of alkanes. What is nitration of alkanes? So you are taking alkane, okay, and you are taking HNO3. So HNO3 in the you are heating it. What you are doing? You are supplying a temperature of 673 Kelvin. Okay, what you yield is nitroalkane. So this is a nitroalkane. Okay. So nitroalkane. So NO2 gets attached to R. Okay, and this is your water molecule. So this is your water molecule. So RNO plus water. So this is what? So this is a nitroalkane. So this is a second properties. What? Nitration. It undergoes nitration of alkanes. Then next is sulfonation. Okay, sulfonation, alkanes plus H2SO4. When you supply a high temperature, okay, what it is? RSO3H. Okay, RSO3H is nothing but your sulfonic acid. Okay, it's your sulfonic acid. So this is your sulfonation of alkane. So this is your third chemical property. So nitration of alkanes, when alkanes, it reacts with nitric acids at 673 Kelvin, it yields what? Nitroalkane plus water molecule. Then sulfonation is of alkanes. Alkanes, when it is reacted with sulfuric acid at high temperature, it yields you sulfonic acid. Okay, so this is the chemical properties. Next, combustion. What do you mean by combustion? When you are heating any compound or a substance in the presence of oxygen. When you are heating, when you are applying very high temperature. Okay, what it yields you? It yields you here. So what you are taken? CH4. CH4 is nothing but your hydrocarbon. Okay, so it is your hydrocarbon. So what it is done? Hydrocarbon in the presence of O2, oxygen. Okay, it is undergoing combustion. What it forms? CO2 and H2O. Okay, so these are the products which is formed. So methane, when it undergoes combustion, it forms carbon dioxide and water. Then next is isomerization. What do you mean by isomerization? The number of or the chemical formula remains the same, only there will be change in the structural formula. Okay, so here you can see isomerization. What happens? You have taken a N-butane. Okay, you have taken a N-butane. So N-butane is taken. Okay, it is treated with what? AlCl3, aluminum chloride, aluminum trichloride plus HCl at temperature of 573 Kelvin at 35 atmosphere. Okay, what it tells you? It tells you a isobutane. Okay, so isobutane, it forms a branched compound. So it is a branched. Okay, so it undergoes isomerization. So in the presence of, this is the conditions you need to remember. So remember this conditions. Isomerization, only there will be change in the structural form. Okay, the chemical formula remains the same. Then aromatization. Okay, aromatization, what is taken? Number of carbon atoms are how many? Number of carbon atoms are 6, right? Number of carbon atoms are 6. So it is C6H4. So it is N-hexane. 6 is hexane. Okay, so in the presence of chromium oxide, okay, and aluminium oxide, at the temperature provided is 773 Kelvin and 10 to 20 atmospheric pressure, it gives you what? It gives you benzene. So aromatization, okay, plus 4H2. So this is a aromatization reaction. So remember the condition. So from N-hexane, with this proper condition, you can prepare your benzene. Okay, similarly N-heptane is converted to toluene. Okay, N-heptane, heptane means what? 7. So 5, 6 and 7 carbons. So it is N-heptane. N, when you write N, when it is a straight chain compound. Okay, so N-heptane, it undergoes aromatization with this following condition and it gives you toluene. Okay, toluene, CH3 benzene substituted with CH3 is your toluene. So this is the another chemical property. So we'll solve this. So of the 5 isomeric hexane, the isomer which can give 2 monochlorinated compound is, yes, of the 5 isomeric hexane, okay, the isomer which can give 2 monochlorinated compound is
Option D, ma'am.
option D. We'll see, just see CH3, CH, CH3, CH, CH3, CH3 gives you, okay, so you have to what you will yield? 2 monochlorinated compound. Okay, so monochlorinated compound, so one you will yield this what is the name? It is answer B. Right. So it is 2,3-dimethyl butane. It is 2,3-dimethyl butane. So from 2,3-dimethyl butane, okay, so one chlorine gets substituted here, okay, at this position, and another gets at this. Okay, so these are the two, because this so this is a secondary carbon and this is a primary carbon. So this is only the stability. So 2 monochlorinated compound yield will be from 2,3-dimethyl butane. So this is the correct answer. Next, pick out the alkane which differs from other members of the group. Yes. The answer is D. What will be the reason? Yes, the answer is D. So the reason here is it has 6 carbon atoms. So in this, it has 6 carbon atoms, while the others have only 5 carbon atoms in their molecules. Okay. So when you see, so which so it differs by other. This is having 5 carbon atoms. Okay, if you write the structures, okay, so this will have 6 carbon atoms, while the other alkanes, they have 5 carbon atoms. So this is the reason. So here in this particular, when you write the structures for all, okay, for the D option, you can see that in this, the number of carbon atoms are 6. Okay, there will be 2 substituted dimethyl, okay, groups. So it will have what? 6 carbon atoms, while the others, A, B, and C, they will have 5 carbon atoms. So this is the reason why it differs from other members of the group. Then the general formula of cycloalkanes. Yes, for cycloalkane, what is the general formula? What is the
Option
general
A.
formula?
Option A, ma'am.
Yes, option A, CnH2n. Okay, it is CnH2n, correct. Next, the reaction conditions leading to the best yield of C2H5Cl. Yes. What is the leading, so which is the reaction? C2H5, so C2H5Cl. Okay, it can be yield from which reaction? So when you take this particular C, right? C, so one of the, okay, Cl2, if you take in excess, and one of the hydrogen will be replaced by your this. So it is C. The correct answer is C. So in the presence of UV light, okay, UV light, so one of your hydrogen atom will be replaced by chlorine atom. Okay. So it will undergo halogenation reaction. Next we'll see is stereoisomerism. Okay. So stereoisomerism, so you know isomerism, they are of 2 types. One is structural isomerism and second is stereoisomerism, right? Structural isomerism we have discussed completely in the last chapter, right? In general organic chemistry. So we have discussed all the structural isomerism. So in this chapter, you are going to study the stereoisomerism. So what is stereoisomerism? The isomers which have same molecular formula and structural formula but differ in their relative arrangement of atoms or groups in space. Okay, so the arrangement of atoms or group in space are called as, so that there is a difference in the arrangement of atoms or group in space. So such isomers are called as stereoisomers, and the phenomena is called as stereoisomerism. So these are of 2 types. First is conformational isomers or conformations, and the second is configurational isomers. Okay, so these are the 2 types. So what is stereoisomerism? So they have same molecular formula and structural formula, but only the difference in the relative arrangement of atoms or group in space. Okay. Then first we'll see what is conformations. So the different arrangement of atoms in space which results from free rotation of groups about CC single bond are called conformers or rotamers or conformations. So conformations, okay. So across the CC bond, if there is the rotation, so what? So there are 2 projections. So first is Sohor's projection and second is the Newman projection. Okay. So what you are doing? You're doing different arrangement of atoms. Okay. By these 2 methods, what you're going to do? You're going to arrange the different atoms in space such across the single bond. So CC bond, okay, it is a single bond. So easily you can twist or you can just rotate the molecule. Okay. So when you are, so one of the molecule is been fixed and another you are rotating across the single bond. So this will develop what? They will form conformers, or they are called as rotamers or conformations. So first is what? First is Sohor's projection and second is Newman projections of ethane. Okay. So what is Sohor's projection? Okay, we are taking the molecule of what? We are considering the molecule of ethane. So what is done here? So in this projection, okay, in this projection, what is done here? See here, the molecule is viewed along. So I'll just draw the Sohor's projection. So you know how the ethane molecule is. So this is ethane. So how do you represent it in Sohor's projection? So draw a tilt line. Okay, then so what is done here? Yes, what is done here? So in this projection, the molecule is viewed along by the molecular axis. So the molecule is viewed from this. This is the molecular axis. Okay, I'll take the color. So here the molecule is viewed from this molecular axis. So these are the molecular axis from which the molecule is viewed. So then it is then projected on the paper by drawing. So we can, so this is the paper presentation. Okay, by paper presentation we are going to draw it like this. So the CC bond is representing this. So this is the CC bond. So these are C. So these are the carbon atoms. So this is a CC bond. Okay, so these are the CC bond. The upper end. So the upper end, this is the upper end of the line is slightly tilted. You can see these are the lines which are slightly tilted, and the front side. So this front carbon is what it represents your this carbon. Okay, this is a front carbon, this is your rare carbon. So this is a rare carbon. So what is done here? Each carbon has 3 lines. You can see these are, each carbon are having 3 lines. So these 3 lines represents what? They are attached to 3 hydrogen atoms. So this is a representation. So it is inclined. So this angles of hydrogen atom, the bonds are they are inclined with which angle? It is angle between them is 120 degree. Okay, it is 120 degrees. So this is a, so this is called as eclipse projection. So how do you get this eclipse? I'll explain you. So this is eclipse and this is staggered, and this is staggered. Okay, now what is done here? So one of the molecule is kept fixed. Now here what is happening? So this carbon atom is falling on the another carbon atom. So they are in the same, they are in the same plane. Okay, so they are in the same plane. So one is behind the another. So it is called as eclipse. So this is the eclipse projection. So carbon, front carbon and the rare carbon, it falls on one another, and their hydrogen atoms also fall on one another. Okay, if you view it from here, okay, if you see it from here, what you can see, it is like this. Okay, it is like this. So what, so this carbon falls on this carbon, this hydrogen falls on this hydrogen, this on this, and this on this. So because of this, it is called as eclipse. So it is getting eclipse. So this is a Sohor's projection of ethane. It is a eclipse form. So how do you get a staggered form? So the front carbon is kept constant. Okay, you are not moving, you are just keeping that front carbon like that, and this you are moving it by you are just moving it by 90 degree. Okay, so what happens when you are moving the rare carbon? So this hydrogen will point downwards. Okay, this hydrogen, it after moving it for 90 degree, okay, you take a turn, rotate it. So what will happen? This will go at the bottom. Okay, these 2 hydrogens. So this so as you rotate this, what will happen here? Just see. So this will come here. Okay, and this will move here, and this will come here. Okay, so this moves here. So like this, it forms a staggered conformation. So this is a staggered conformation. So Sohor's projection of ethane. So it will form 2. This is eclipse projection. This is a staggered projection. So in between, whatever is formed, so this is a Sohor's projection of ethane. So what is done? Different arrangement of atoms in space, which results from the free rotation of groups. So you are rotating the groups around the CC bond. So around this carbon-carbon single bond, you are rotating the atoms. So this is, first one is Sohor's projection of ethane. One is eclipse, another is staggered. Then What is Newman projection? The same. The same is explained in the form of what? So first we'll see what is the order of stability. So staggered is always stable, then eclipsed. Okay, staggered form is stable, then your eclipsed. So your staggered form, this is a staggered formation. What I had drawn here, so this is a staggered formation, and this is a eclipse formation of ethane. So next we'll see what is Sohor's projection. So these are the Sohor's projection. So how we had represented our ethane in Sohor's projection? This is by Newman projection. So Newman projection, how do you write? So the rare carbon, okay, the front carbon is here. So front carbon with its hydrogen. The rare carbon is this. Okay, rare carbon with the hydrogens. So this is which form? This is a eclipse form. So one behind the another. So this carbon is behind this carbon, hydrogen atoms. Okay, they are falling one behind the other. So these are called as eclipse form. And what do you mean by staggered form? So same here, what you're doing. Okay, so this is the front carbon. So I'll draw the front carbon. What I'm going to do, I'm just going to keep this front molecule of CH3 like that only. And what I'm going to do, the rare carbon is there, that I'll just rotate. So after rotating, what will happen? That hydrogen will come here, okay, and it will take this position, and this is called as staggered form. So this staggered form is it is more stable. Why? Because there is no this, okay, so there is angle of rotation or the torsional angle or the dihedral angle. So there is what? There is no what you say, steric hindrance. Okay, there is no steric hindrance. There is no steric hindrance. So there is much the atoms are far apart. So the atoms are far apart. So they will have this is a more stable form, staggered conformation of ethane. So in between, so this is eclipse and this is staggered. So in between also there is one form called as Q. Okay, it is called as Q formation conformation, but these two are important. So the stereoisomers, they can be of two types. One is Newman projection, another is the your Sohor's projection. So remember what is staggered form, what is eclipse form. Next, we'll see the preparations of alkenes. Okay, so we have completed the preparations and physical properties, chemical properties of alkanes. Now we'll start with alkenes. Alkenes, so from alcohols. Okay, alkenes can be prepared from alcohols. How they are prepared from alcohols? Dehydration of alcohols, right? So dehydration of alcohols. So ethyl alcohol is taken, ethyl alcohol in the presence of concentrated H2SO4. Okay, concentrated H2SO4, here the temperature is 443 Kelvin. What you yield is ethene. Okay, you yield your ethene molecule plus water molecule. So this is a dehydration. Dehydration is what? Removal of water molecule. So removal of water molecule is your dehydration. So from alcohols, your water molecule is getting removed. Okay, so it is forming ethene. Then from alkynes, by controlled hydrogenation. So by controlling the conditions, by controlling the conditions, you can form your alkynes. So hydrogenation in the presence of Lindar's catalyst. Remember this, very important. So hydrogenation in the presence of Lindar's catalyst gives you what? It gives you a cis. Okay, it gives you cis alkanes, while bridge reduction gives you trans alkene. So Lindar's catalyst. So when you are if you want to prepare your alkenes with the control hydrogenation, if you want cis alkanes, it will give you what? From Lindar's. Okay, from Lindar's catalyst, it gives you cis alkenes, while from bridge reduction, it gives you trans. Now, what is this cis and trans? Okay, we'll see. So here, this is the first one. So alkyne, you are taken alkyne. Okay, triple bond, you can see alkyne. So in the presence of Lindar's catalyst, what do you mean by Lindar's catalyst? PD. Okay, palladium in the presence, or barium sulfate plus quinoline. Okay, so this is a Lindar's catalyst. It gives you cis alkene. So what is cis alkene? Across the double bond. Across the double bond, if the two atoms, okay, if the two similar atoms are occupying at the same side of the double bond, then that is cis alkene. So across the double bond of the carbon atoms, if the two same atoms are at the same position, at the same side, okay, bond, then they are called cis alkene. And across the double bond, here you can see across the double bond. So this is a double bond, CC double bond. So across this double bond, if the two atoms are occupying the adjacent position, then they are called as trans alkene. So when do you get trans alkene? When you are doing bridge reduction, okay? And when you are getting cis alkene, when you are doing with the Lindar's catalyst. So remember which is the catalyst. So from alkyne, if you take sodium, this is what sodium in liquid ammonia, okay, sodium or liquid ammonia in the presence of ethanol, okay, the condition is 100 Kelvin bridge reduction. So this is the condition in bridge condition, okay, bridge reduction to what? Trans alkene. Everybody else, please mute yourself. Yes, thank you. Okay, so when you want to get a cis alkene, what you are going to use? You are going to use Lindar's catalyst. Okay, you are going to use Lindar's catalyst. So, and if you want to yield a trans alkene, you have to use a bridge reduction. So remember these conditions. Okay, remember which is the catalyst used, which are the reagent used, and what is the different conditions. So this is the reaction to obtain cis and trans alkene. So dehydrogenation, okay, dehydrohalogenation of alkyl halides using alcoholic KOH. Dehydrohalogenation, okay, dehydrohalogenation. So you see here, alkyl halide. What is alkyl halide? So this is the alkyl halide in the presence of alcoholic KOH. Okay, in the presence of alcoholic KOH, what it is obtaining? It is obtaining. You are obtaining a alkene. So this is you are obtaining the alkene. So these are what? These are all hydrogens. Okay, alkyl halide. Okay. So what is happening here? Right. So this will form one. So like this, your so like this, your alkyl halide will go. Okay, HX will go. So like this, you will form a double bond. So like this, your double bond will be formed. This is your HX. Okay, this is HX. So it will form what? Okay, so this is the alkyl halide. So example is given here. Okay, example is given here. So ethyl bromide. Okay, ethyl bromide, what it will yield you in the presence of alcoholic KOH, it yields you ethene, C double bond O. Okay, then this K will get attached to this K. Okay, Br, and it forms KBr plus OH. OH remains. Okay, and this hydrogen which is removed will be added with this water molecule. Okay, so this is your dehydrohalogenation. Okay, dehydrohalogenation. One halogen atom and this two H2 molecules are removed. So this is what? This is a dehydrohalogenation. So which is the reagent used? It is a alcoholic KOH. Remember, very important, alcoholic KOH is removed. It is used for dehydrohalogenation reactions. Next, dehydrohalogenation of vicinal dihalides. What is vicinal dihalides? What do you mean by vicinal dihalides? That is when two halogen atoms are on the neighboring carbon atom. So when the two halogen atoms, okay, so these are the two halogen atoms which are on the same, okay, different here, neighboring, you can see. So these are the halogen atoms are on the neighboring carbon atom. So this is called as vicinal dihalide. So 1,2-dibromoethane in the presence of zinc and alcohol. Okay, in the presence of zinc and alcohol, it gives you what? It gives you ethene. So this is a ethene plus ZnBr2. Okay, so this is the reaction. So dehydrohalogenation, same. Here also what happens? Okay, first one molecule will go and then your second will go. Okay, so like this dehydrohalogenation reaction will takes place. Next, at room temperature, the eclipsed and staggered forms of ethane cannot be isolated. Why? Of ethane cannot be isolated because at room temperature, the eclipsed and staggered forms of ethane cannot be isolated because the answer is that they interconvert rapidly. Okay, they cannot be isolated because they interconvert rapidly. So at room temperature, this eclipsed and staggered forms of ethane cannot be isolated because they interconvert rapidly. Okay. Next, hex 2-ine gives trans hex 2-ine on treatment with sodium in liquid ammonia. Yes, what is sodium in liquid ammonia? So when you obtain yes, what is the condition here? Sodium in liquid ammonia, right? So when sodium in liquid ammonia is there, you obtain your trans alkene, right? The question is wrong there. Question is wrong. So, yes, so alcoholic KOH is used to bring about, yes, alcoholic KOH is used when, which type of reaction? When it is used, alcoholic KOH?
Option C, ma'am.
Yes, for dehydrohalogenation. Okay, for dehydrohalogenations. N-propyl bromide on treating with alcoholic KOH produces N-propyl bromide on treating with alcoholic KOH provides, so it will be CH3, CH2, okay, N-propyl bromide, okay, in the presence on alcoholic KOH is to what? Propene,
Option
right?
B,
Answer is
ma'am. Option B, ma'am.
it is propene. We are preparing propene, not propanol. From dehydrohalogenation, right? It is D. The answer is D. Okay, your the answer is propene, not B. It is propene. Okay, it will undergo dehydrohalogenation reactions. 1-phenyl-2-chloropropane on treatment with alcoholic KOH. So we'll write the reactions. Just see. So 1-phenyl. So it is C6H5, CH2, CH, Cl, CH3 in the presence of alcoholic KOH. What it obtains? C6H5. Okay, one of this will go. So it will be CH double bond. Right. So this will form, this will go. So what it will be? Double bond CH and CH3. So what it is? 1-phenyl propene, right? 1-phenyl propene. So answer is D. So 1-phenyl propene. Answer is 1-phenyl propene. Understood? So next, chemical properties of alkenes. So bromination. So propene, when you react with Br2, okay, when you react with Br2, in the presence of CCl4, carbon tetrachloride, okay, at the double bond, you can see across the double bond, both the halogen atoms will, okay, so so here what is happening here across the double bond? So across this double bond, what is happening? Your Br are getting added. So it is 1,2 dibromopropane. So you are removing this okay, double bond is there. So one of the bond is been what is breaking of this bond takes place, and across this bond what will happen? Br will get added. So this is a bromination. So this test is normally used for test for unsaturation. Okay, this test is used for testing the unsaturation, that is presence of double bond or triple bond. This the discharge of orange color of bromine indicates the presence of double bond. So if your compound, okay, if it reacts with bromine and it gives you orange color, that means there is unsaturation present. That means there is double bond or triple bond present in your compounds. Okay, so this test tells you about unsaturation. So addition of water, so across this double bond, what is happening here? So CH2 double bond CH2. Okay, you are adding your water molecule. Water, how it is? Water H plus and OH minus, right? So in the presence of H2SO4, okay, H2SO4, what is happening across the double bond? So one of the bond you just remove and add here one H and here one OH. So anywhere you can add OH and anywhere you can add H, because why? Because what is happening? It is a symmetrical alkene. Okay, it is a symmetrical alkene. So you can add hydrogen towards one carbon atoms and OH towards one carbon atom. So it forms what? Ethanol.
Yeah,
It is.
Huh?
So this is addition of water takes place. Please mute yourself. So addition of halogen acid. Okay, addition of halogen acid is what? It's HBr. So what you are doing? Addition of halogen acid. So this is a unsymmetrical alkene. Unsymmetrical alkene means what? Number of carbon atom across the double bond is what? It is number of carbon atoms across the double bonds are different. They are not same. So it is a what? So whenever there is unsymmetrical alkene, so addition, so whenever you have symmetrical alkene, so across the double bond, wherever you want, you can add one hydrogen and another one OH, right? Last example we had seen, last reaction. So when we were adding water across a double bond, when it is a symmetrical, so across a double bond, at one carbon atom you can add a hydrogen, another carbon atom you can add OH. Now whenever there is an unsymmetrical alkene, okay, whenever there is an unsymmetrical alkene, what happens to unsymmetrical alkene? So addition of hydrogen halide. So how you will decide it? It is decided on the basis of Markovnikov's rule. Okay, it is decided on the basis of Markovnikov's rule. Now, what is Markovnikov's rule? Okay, so whenever you have unsymmetrical alkene, so addition of alkyl halide. So addition of this halogen acid or alkyl halide, this halogen acid takes place such a way that the negative part, okay, this negative part, so this is what? H plus and this is Br minus, right? So across the double bond, so across the double, so whenever you have unsymmetrical alkene, so addition of this halogen acid, so the Br minus, the negative part, it is added to the carbon having less number of hydrogen atoms. Okay, so this is Markovnikov's rule. So whenever you are adding this halogen acid across the double bond in an unsymmetrical alkene, so the negative part, so which is negative part? Br is added to the carbon having less number of hydrogen atoms. So now this is a propene. So across this double bond, you can see this is CH. So it is having only one hydrogen and this is having two hydrogen. So the negative part, this is Br. So Br will be added to which? Br will be added to the carbon having less number of hydrogen atoms. So Br will be added to this and hydrogen atom will be added to the carbon having more number of hydrogen atoms. So this is Markovnikov's rule. So this will be the major product. Okay, it will form both the it will form CH3, CH2, CH2, Br also, but this will be a minor product in case of Markovnikov's rule and this will be a major product. So you know major product and minor product. So this is a major product. So Markovnikov's rule states what? Whenever you have an unsymmetrical alkene, so across the double bond, the negative part will be added of the halogen acid will be added to the carbon having least number of hydrogen atoms. So this is your Markovnikov's rule. Okay. Now, what is anti-Markovnikov's rule? Anti-Markovnikov's rule is what? It is vice versa. So, okay. So, when anti-Markovnikov's rule takes place in the presence of what? Peroxide. Okay. So, if it is a peroxide is there, so on this arrow, what will be added? So, there will be unsymmetrical alkene. There will be a halogen acid on, and on the arrow, there will be, they will write peroxide. So, in the presence of peroxide, it will undergo anti-Markovnikov's rule. Anti-Markovnikov rule is what? Addition of this halogen acid. Okay. So whenever there is an unsymmetrical alkene, so across this double bond, the negative part of the halogen acid it is added to the carbon having more number of hydrogen atoms. It will be vice versa. Remember, okay, Markovnikov's rule, negative part will be added to the across the double bond of the alkene, okay, where the number of halogen to the carbon having least number of hydrogen atoms. So in the presence of peroxide, it will undergo what? It will undergo anti-Markovnikov's rule. It will be vice versa. So in anti-Markovnikov's rule, what will be the major product? It will be CH3, CH, okay, so CH2, right? So where it will add in the, so how it will be? So H peroxide plus HBr. Okay, so whenever peroxide is there, means it is anti-Markovnikov. So what you will get? So HBr will be added to the carbon having more number of hydrogen atoms. So this will get H2 and this will be CH2Br. So this is what? This will be a major product in case of your anti-Markovnikov's rule. So remember Markovnikov's rule and anti-Markovnikov's rule. Anti-Markovnikov rule, they will not give you right according to anti-Markovnikov rule. You have to see whenever there is an unsymmetrical alkene, there is a halogen acid and they will write peroxide, okay, on the arrow, then it is anti-Markovnikov. And there is no peroxide, there is unsymmetrical alkene and HBr is written, then you have to follow the Markovnikov's rule. Okay, so this is very important, Markovnikov's and anti-Markovnikov's. Next is ozonolysis. So across the double bond, what we are adding? We are adding a molecule of ozone. Okay, we are adding a molecule of ozone. So this is alkene. Okay, R, CH, double bond, CH. Okay, and R. So this is a symmetrical alkene. So across this double bond, so what we are doing? We are breaking this one bond. Okay, so across this bond, what is happening? This takes place. Breaking of this bond takes place. So how they have written just here. So what you are going to do? You are going to add a molecule of O3. Okay, you are going to add a molecule of O3. So C, okay, C, then this is R, this is attached to H. Then, so across this bond, okay, across this bond, O3 will add. So O, okay, oxygen here, then this is oxygen. So O3, 1, 2, and 3 oxygen molecules are added. Like this, okay. So this is a ozonide. So this formation is called as ozonide. So this is called as ozonide, and then it is reduced. So in the presence of zinc and water, you get aldehyde. So that you get zinc and water, you get aldehyde. Okay, so like this. So you get zinc and aldehyde. So C. So here you can see. So RCHO. Okay, RCHO. So like this, you get a one bond between CO here it breaks and one bond between CO it breaks here. Okay, so you get this. This is a product what is obtained. So it is a aldehyde. So ozonolysis takes place. That is, ozone is added across the double bond. Okay, a molecule of ozone is added. Next, which of the following reaction would yield 2,2-dibromopropane? So which of the reaction will yield 2,2-dibromopropane? Yes. Which reaction will yield 2,2-dibromopropane? It is the reaction is D. Okay, how D? I'll show you. CH3, C, triple bond, CH plus 2HBr. Okay. So what is happening here? So first it will be CH3C. Okay. So Br will be added to the carbon having least number of hydrogen atoms. So across this, so this will have. So then you will get what? CH2. Then 2HBr is there, right? 2HBr. They are what? 2 dibromo. Okay, 2 bromo should be added. So again, one more molecule. So this is only one HBr is added. Then another molecule of HBr is taken. Okay, so here only one molecule first is taken to be more of this. Then CH3, then C. So again, least hydrogen will be for here only. So it will be here. Okay, and then it is CH3. So this is the answer D. Okay, so like this you are going to solve. So this is what? This is a Markovnikov's rule. Geometrical isomerism. Yes, so next is geometrical isomerism. So geometrical isomers, we have discussed this. So they have same structural formula, but they differ in the spatial arrangement of atoms or group of atoms about the CC bond. Okay, C double bond C, C double bond N, or N double bond N double bond. Okay, so across this, there is a difference in the spatial arrangement of atoms. So I said you, so similar groups on same side of the double bond are called as cis. So you can see here the X, okay, the atoms are on the similar. Okay, here you can see, so here also X are on, so here they are on adjacent or different side of the double bond. So here they are on similar side, similar groups on same side of the double bond. So on the same side, these are present. So if the groups are on the same side of the double bond, then it is said to be cis. And if the similar groups are on the different side of the double bond, so you can see here they are on the different side, XS, XX atoms or groups are on the different side of the double bond, then they are called as trans. Okay, then it is cis and trans. So these are called as geometrical isomers. So which of the following compounds will exhibit geometrical isomerism? So you have to write the structures and then you have to see which you will go. Okay. So the correct answer is A. A is the correct answer. I'll just write C. Okay. This is the structures of 1-phenyl but-2-ene. Okay. So this is the correct structure. So this is the geometrical isomerism it will show. So one of the compound which will show exhibit geometrical isomerism. So these are on the same side. So it is cis. Okay. And if you write on the other side, if you write both the like this, then it is trans. Okay. So like this, you are going to write the geometrical isomerism. So A is the correct answer. The alkene that exhibit geometrical isomerism is, yes, which is the alkene which will exhibit geometrical isomerism. A, right? Answer is 2-butene. So on the same side, cis, on the what is that? Opposite side, then it is trans. Okay. So this is the geometrical isomerism. Next, alkynes. Okay, next is alkynes. So this is the preparation of laboratory method. So from calcium carbide, when you treat it with water, you get ethyne. Okay, you get ethyne, CH triple bond, CH. Okay, so this is what? So it is a triple bond. Okay, ethyne, carbon having carbon-carbon bond having a triple bond. So this is CnH2n minus 2. What is the formula here? General molecular formula, it is CnH2n minus 2. And for alkenes, alkene it is CnH2n. Okay. So here, what is the laboratory method? Calcium carbide treated with water molecule. It yields you ethyne and calcium hydroxide. So next is dehydrohalogenation of dihalides. Okay. So dihalides, so vicinal dihalides, you know, so on the neighboring carbon atoms, halogen atoms are present. Okay, so halogen atoms in the presence of alcoholic KOH, it yields you what? It yields you ethyne, 2 kBr and two water molecule, dehydrohalogenation. So dehydrohalogenation important, which is the reagent used, it is alcoholic KOH. So from dehydrohalogenation of dihalides, you can yield your alkynes. By treating tetrahalides with zinc dust. Okay, by treating tetrahalides with zinc dust, CHCl2, CHCl2, what is it? It is 1122 tetrachloroethane. Okay, 1122 tetrachloroethane. When you are treating it with zinc dust, you get ethyne and zinc chloride. You get what? Ethyne and zinc chloride. So this is the preparation from which you get your ethyne. Then by heating it with iodoform with silver. Okay, so this is iodoform CHI3. Okay, CHI3. So CHI3, that is 3 molecules, 3 atoms of hydrogen are replaced by I3. Okay, iodine atoms. So plus 6 Ag silver is taken. So there are 2 molecules of iodoforms are taken. Okay, 2 molecules of iodoforms. They react with silver. Okay, they are heated with silver, and you get what? Ethyne plus silver iodide. Okay, you get ethyne plus silver iodide. So the reagents for the following conversion. Okay, this is the reaction. Okay, the reagent used for following conversion is, which is the reagent used here? One two dibromoethane, right? 1,2-dibromoethane. It is treated with what? To give you ethyne. It is what? Dehydrohalogenation reaction, right? It is what? Then you have to. So it is alcoholic KOH. Correct. The answer is D. Alcoholic KOH followed by NaNH2. Okay, NaNH2. The correct answer is D. Alcoholic KOH followed by NaNH2. So I'll just write the reaction. So it is CH2, okay, Br, like this. They have written in the bond length structure. Okay, 1,2-dibromoethane. It is treated first with alcoholic KOH. You get what? Br, CH, double bond, CH2. Then what you do? You treat it with NaNH2. Okay, sodium amide. Okay, sodium amide. Then you get what? CH, triple bond, CH. So this is the reaction. So this chemical properties we'll study in the next class. Okay, so we'll stop it for today. So we had discussed the preparations of alkanes, chemical properties, physical properties, right? Then we saw the stereoisomerism. Then we have discussed the physical properties, chemical properties of alkenes. Then we have seen the preparations of alkynes. So chemical properties and rest of the part we'll discuss in the next class. Okay, thank you. Thank you, students. We'll meet in the next class.